Can everybody see my screen now? Okay, great. All right, thanks, Ryan. All right, so there's the answer to question number 3 above. There we go. Okay, so let's get into question number 4. Draw and name the 2 constitutional isomers of C4H10. Well, we could start by just drawing a linear hydrocarbon. So 1, 2, 3, 4, like that. This would be butane. The only other way to connect 4 carbons would be like this, have 1, 2, 3, and have one branched off like this. This molecule is called 2-methyl propane, right? Because the longest carbon chain has 1, 2, 3 carbons, and then we have a methyl group on here, so that's where we get 2-methyl propane. It also has a common name. The common name is isobutane, so isobutane. I don't expect you to have that memorized, but just in case you want to know. All right, let's try some nomenclature problems, and these are naming hydrocarbons. Take a look at the first one. The longest carbon chain in this molecule is, I think, rather easily identifiable. Okay, it's got a total of 1, 2, 3, 4, 5, 6 carbons, so it must be some kind of hexane. And then we have a methyl group here and a methyl carbons 2 and carbon 4. And so this molecule is 2,4-dimethylhexane. All right, let's try the next one. The next one, if we want to identify the longest carbon chain, is 1, 2, 3, 4, 5, 6, 7 carbons in it like that. Now you can see we have a methyl group here, and here we have a tert butyl. We number these 1, 2, 3, 4, 5, 6, 7. This is some kind of heptane. And we have a 2-methyl. And we have a 4-tert-butyl. Remember that we ignore all prefixes except iso, cyclo, and neo. And so butyl is going to come before methyl. That means when we put all of this together, I'll just move this one up here. That's going to give us 4-tert-butyl 2-methyl heptane. All right, let's try the last one. Find the long carbon chain, which has 1, 2, 3, 4, 5 carbons in it. So this is some kind of pentane, right? 1, 2, 3, 4, 5. We've got 1, 2, 3, 4 methyl groups. So this is a tetramethyl. And it is more correctly 2, 2, 4, 4 tetramethyl pentane. Because there's 5 carbons. 2, 2, 4, 4 tetramethyl pentane. Number 6, draw the correct line angle, which is the same thing as bond line, structure of 8-ethyl-2,3-dimethyl decane. So our parent is decane. That means it's got 10 carbons. So let's just do this. 1, when our pen touches the ground or touches the page or touches the screen, that's the first carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. On carbons 2 and 3, we have methyl groups. And on the 8th carbon, we have an ethyl group like that. There we go. And there's the structure of our compound, 8-ethyl-2,3-dimethyl decane. The next question has to do with intermolecular forces. It says, circle the molecule that you would expect to have the lowest melting point and explain why. Well, the molecule that has the lowest melting point is going to be the one that has the weakest intermolecular forces, IMFs. Now we need to consider what are the types of forces that would be present in these compounds. Well, every kind of molecule is going to have London forces, but the molecule on the top has a hydroxyl. right? So not only does it have London forces, but it also has hydrogen bonding, right? And it's also going to have dipole-dipole forces. These two here are just plain old hydrocarbons. They only contain carbon and hydrogen. Remember that a carbon-hydrogen bond and a carbon-carbon bond, these are non-polar. Okay, those are non-polar bonds. So that means both of these molecules are completely non-polar. What's the only intermolecular forces they're going to experience would be London forces and London forces. So London forces are weaker than hydrogen bonds or a dipole force, dipole-dipole force. Which one of these is going to have weaker London forces? The one in the middle or the one in the bottom? Can anybody tell me? Yeah, it's the one in the middle. Why? Because it's the smallest one. So only London forces and smallest molecule. So it's going to be easiest to break the intermolecular forces and cause that compound to melt. Question number 8, I think, is kind of a challenging problem, especially when there's no answer to choose from, right? It's not a multiple choice question. It says, what type of isomers are the following molecules to each other? There's a couple of ways you could identify this or differentiate between these two molecules. I'll give you a second to think about how you would differentiate between them, what type of isomers they are. But could we name the molecules, right? What's the parent in both of these? They both are a cyclobutane. Okay, they both have a cyclobutane, but the first one, you see the two methyls at carbons 1 and 3, those are on the same face of the molecule. And so this must be cis 1,3 dimethyl cyclobutane. And this molecule here would be trans 1,3 dimethyl cyclobutane. So they only differ in the placement of one of the methyl groups and how it's oriented in space. So yeah, they're cis and trans, but could you tell me what type of isomers these would be? Does anybody have an idea? Besides cis, they're not cis-trans isomers. It's not really the correct way to describe them.
Are these stereoisomers?
Absolutely, 100% correct, right? These are stereoisomers. Stereoisomers, because they differ not in the connectivity, but they differ in the arrangement of the atoms in space. Now, I would give that 100%. I'm not sure who answered, but I would give that 100%. Now, more correctly, these would be diastereomers. And I did cover diastereomers in class briefly. And I said that diastereomers are stereoisomers that have at least one chiral center that's different. Okay, so more correctly, they would be diastereomers, but I would say stereoisomers is a perfectly reasonable answer. Okay, and it's a correct answer. Question number 9, write the condensed structure formula of 3-nonene. Well, I like to draw bond line structures. So I'm going to start by drawing the bond line structure of 3-nonene. I'll start with 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. I look carbon 1, 2, 3, and on the third carbon, I'm going to have a double bond like that. But that's not a condensed structure, is it? A condensed structure shows the atoms, but it eliminates carbon-hydrogen in single carbon-carbon bonds. What do I mean by that? I'm going to have CH3, CH2, CH, you have to show the double bond. CH, I'm right here right now. I have 1, 2, 3, 4 methylenes or CH3s. So why don't I put those CH2s, CH2, and I'll put 4 of them like that, and then I'll put a CH3 like that. And that would be a perfectly good condensed structural formula for 3-nonene. Let's try naming these two molecules. These do fall under the cis and trans umbrella, don't they? Because this molecule here has 2 hydrogens that are trans to each other, and this one has 2 hydrogens that are cis to each other. Well, if we look at the longest carbon chain, it has 1, 2, 3, 4 carbons in it. Why did I start numbering right here? Why did I not start numbering where the number 4 is? The reason why is because I have one substituent. I have a bromo, and I want to give it the lowest possible number. I also want to give the double bond the lowest possible number, but it wouldn't matter if I put my number 1 here and number 1 here. The double bond would still be having a locant of 2. So that makes this molecule here on the left 1 bromo, trans, 1 bromo, 2 butene. All right, same. We have,
Question.
go ahead.
When you're naming these compounds like in front of us, do you prioritize the substituents or the double bonds as far as the lowest number?
So the double bond is, since these compounds are both alkenes, that's part of the parent, right? The way that you identify that these are alkenes is from the suffix -ene in butene. Okay, so the locant for the alkene has to come right before the parent name. Okay, that's one of the rules of nomenclature. Okay, so the substituents always come first, right? The locant for the substituent, and then the locant for the double bond in the longest carbon chain is always going to come last. All right, so same strategy for the compound on the right. We have 1, 2, 3, 4. So this is simply going to be cis, 1 bromo, 2 butene. All right, here we go. Well, a little bit more nomenclature practice. Here we have 2 alkenes and an alkyne. They don't look that simple, but we can tackle these for sure, especially the first one. Just an alkene, we find the longest carbon chain, which is, again, pretty easily identifiable since there's no branching occurring. But we're going to want to number it starting on this end because that will give the double bond the lowest possible number. So we'll go 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. Now, I know we didn't look at a whole lot of 12 carbon chains, but when you have 12 carbons in a row, that's called a dodecane. Okay, so this would be a dodecene. It goes decane, undecane, dodecane. Anyhow, so this is a dodecene. Anyhow, so this would be a 3 dodecene. And then what's the geometry here? It's trans, right? Because the 2 hydrogens are trans. So this is trans 3 dodecene. The next one is an alkene as well. We count 1, 2, 3, 4 for our longest carbon chain. If you had gone up here for number 4, or if you'd gone down here for number 4, either way, you're going to get the same answer. So this is a 1 butene. 1 butene. Okay, that's my parent, right? 1 butene. And I have 2 methyl groups, and they're both on the 3rd carbon. So this is a 3 dimethyl, 1 butene. Excuse me. And the last one is an alkyne. The longest carbon chain, 1, 2, 3, 4, 5, 6. Okay, it has 6 carbons. If I was to start numbering from here, I'd have 1, 2, 3, 4 for my alkyne, for my locant. So if I start numbering here, 1, 2, then I have 2. So 1, 2, 3, 4, 5, 6. Remember how the rules go. First, you identify the longest carbon chain, and then if it's an alkene or an alkyne, you try to give the double or triple bond the lowest possible number. So we've got that part done. So we know that this is a 2-hexyne. We could even write that down. Just say this is some kind of 2-hexyne, and then we just need to list the substituents. Here we have a 1 iodo, and here we have a 4 methyl. Well, that's pretty easy. I comes before M in the alphabet, and so this is 1 iodo, 4 methyl, 2-hexyne. Bada boom, bada bang. All right, who's feeling a little bit better about nomenclature now? A little bit of a review. I hope somebody is. All right. Good. Great. All right. Review's never a bad thing. All right. Well, let's try number 14. It says draw the structural formula for 2,2,4-trimethylpentane. Look, the parent is a pentane. We could just start with that. Say if you look at this and you're like, oh man, what is this? How do I draw that? Look, just start with the suffix pentane. 1, 2, 3, 4, 5. There you go. So you've got the first part done that fast. 1, 2, 3, 4, 5. You can number the carbons if that helps. 1, 2, 3, 4, 5. At carbon 2, you've got 2 methyl groups, so 1, 2, and at carbon 4, you have 1 methyl group. There you go. That's it. Nothing more than that. That's the structural formula for 2,2,4-trimethylpentane. Number 15 says, or asks, which would you expect to have a higher boiling point? 2-methylbutane. So let's start by drawing that. 2-methylbutane, which is 1, 2, 3, 4 for a butane. Then on carbon 2, we'll put a methyl, or pentane, which is just this 1, 2, 3, 4, 5. They both have the same molecular formula, right? Both are C5H12. They're both saturated hydrocarbons. Can anybody tell me which one would have a higher boiling point? So greater intermolecular forces?
Would it be 2-methylbutane because there's more branching?
You're in the right vein, but you got it opposite. So the more branching you have, it's going to have a lower boiling point. Right? Think about it this way. The more closely the molecules can pack together, the stronger the intermolecular forces will be, and the harder it will be to pull them apart. Right? It gets harder to tear them apart and get them to boil. Right? Whereas if you have another molecule of 2-methylbutane, right, it's not going to pack very efficiently. Right? It's not going to pack efficiently at all, in fact. And so it's going to have a much lower boiling point, right? It's going to be a lot easier to separate those molecules. Does that make some sense?
Yeah, I just got it mixed up. Thank you.
Yeah, no problem at all. So this is going to have a higher boiling point due to, let's write it like this, due to increased surface area, therefore stronger, I shouldn't say stronger intermolecular forces. I mean, the net, I'll say, therefore greater net intermolecular forces. Okay, still the same type of intermolecular force. It's just overall, it's going to be stronger. Okay, what's next? I'm looking at my answers here, and I see I have a mistake in them. Anyhow, I'll write that down. There we go. So I'll fix that. Let's get on to the next question. Where's my pencil? Draw possible products that will form when the following molecule is dehydrated in the presence of a strong acid. We get a strong acid, and we're heating it up. Label the major product, the Zaitsev product from the reaction. Okay, so remember, if we're doing a dehydration reaction, that means we're going to lose water in this reaction, right? We're going to lose water somehow. Where's the water going to come from? It's going to come from OH, and then in H2O, I need another proton. That proton can either come from here, and I can make a double bond there, or it can come from here, and they can make a double bond there. Remember, this is the carbonyl-carbon. Okay, carbonyl-carbon. So you can go to the carbons that are next to it, the ones that are attached directly to it, this one and this one, and you are allowed to pull protons from those. So if I pull a proton from the carbon on top, why don't I use yellow? No, that won't work. Why don't I use blue? Okay. If I pull a proton from there, what am I going to have? I'm going to have CH, CH, CH3. I'm going to have a double bond here. CH, methyl, and a methyl. If I pull it from here, from that carbon, what am I going to have? I'm going to have my CH, C, I'm going to have a double bond. It's going to have these two methyls directly attached to it, CH2 and CH3. So I got two products written here. Can anybody tell me which one of these is the Zaitsev? Is it the blue one or the green one? Would the Zaitsev product, the major product, be the blue one or the green one? Well, the answer is it would be the green one. This is going to be the major product. Why? Because this double bond is more substituted. That double bond, you look at the two carbons in that double bond, they're attached to 1, 2, 3 carbons overall. If you look at the double bond here, these two carbons are attached to 1, 2 carbons overall. The more substituted a double bond is, the more stable it is. And so this is the major product or the Zaitsev product. And this would be a minor product. This is why review is a good thing, right? Okay. Let's take a look at number 17. Draw the possible products that will form when the following molecule is reacted with HCl. Predict the major product. Okay, so this is a Markovnikov addition, right? We are adding HCl. One of these carbons is going to take the hydrogen, and the other one is going to take the chlorine. Remember the rule for Markovnikov addition. The rich get richer. It's like what's happening now. If you have a small business, you're going down, but if you're Costco, you're killing it, right? Okay, so which one of these carbons is richer? This one has 1 hydrogen, and this one has 0 hydrogen. So it's pretty obvious which one of these is richer. And so this carbon is going to take the hydrogen, and this carbon is going to take the chlorine. So let's just draw the structure of the product, which is going to look something like this. Does that make sense? Give me a thumbs up if you follow me on that one. Markovnikov addition. I can't stress it enough. You have to know Markovnikov addition for the final exam. All right, great. Well, let's try some more nomenclature. Now we're looking at aromatic compounds. And there's a couple of ways that you could name the first one. In fact, there's several ways you could name this compound. All right, well, let's start by tallying up the carbons in the aromatic ring. We'll go 1, 2, 3 like this. Remember, there's a plane of symmetry in this molecule. So probably the easiest way to name this is as a derivative of benzene, right? Because when you have a 6-membered ring with alternating bonds like this, this is called benzene. Benzene. So we could call this 1,3 dimethyl benzene. That would work. Since it's di-substituted, another way that you could describe this would be meta dimethyl benzene. So you could call it meta dimethyl benzene. That works. And then it also has a common name if you Google it, which I would never expect you to. Actually, no, maybe we did look at xylenes. I don't remember. Anyhow, its common name is metaxylene. Either way, that's not going to come up on the final. I'm not going to ask you about naming xylene. All right, let's take a look at the next one. So the next one, we have an aromatic ring. We've got 3 substituents. Remember, we number it such a way to give the lowest possible number. So at the first point of difference, so we go 1, 2, 3, 4. Right? If we had gone from the top like this, 1, 2, 3, then we have 1 and 3 and 4, and 2 is a lower number than 4. So we go 1, 2, 3, 4. So we've got a tert-butyl here. We've got 2 bromines here. So we have 1, 2 dibromo and a 4 tert-butyl. Well, remember, we ignore all prefixes, di, tri, so on and so forth, tert. So the bromo is going to come before butyl. Br comes before Bu. So this would be 1, 2 dibromo, 4 tert Running a space here. Butyl, still, benzene, that. And the last one is tri-substituted. Tri-substituted. Well, here it looks like you've got, you know, how are you gonna name it, right? Are you gonna name it going this way, 1, 2, 3, or the other way around? Well, I got an answer for you. Could anybody name the parent that I'm circling here? If you have a benzene with a methyl group on it, could anybody name that molecule? We looked at it a few times. Got a common name. Thanks, Greg. Perfect. Yeah. Killing it. Toluene. Absolutely. So why don't we name this as a derivative of toluene? All right, so this butyl group will be, in the second position, and the iota will be in the third position, right? The methyl is considered 1 if we name this as a toluene derivative. So if it's 2 butyl and a 3 iota, so this becomes 2 butyl, 3 iodo toluene. Look, I just want to stop for 1 second here and tell you something before we keep going. Okay, if you're panicking, and I hope that nobody is panicking, I hope you're just thinking, hey man, I need to review my OChem. It's totally normal at the end of a long semester. I consider these questions definitely not uber difficult, but I put them in here on purpose to make you think. Okay, now don't go and say, hey, Mr. Deon said the final exam is super easy. No, I don't think the final exam is easy, but I think it's a little bit simpler than these questions. Okay, I'd say it's an order of magnitude less complex than these. So these are good kind of brain benders to kind of get you thinking. Some of them are probably in the exact same level of complexity. Anyhow, write the condensed structural formula of 3-methyl 1-pentanol. I love these ones because when I'm given a parent, right, it's got 5 carbons. Look, I just start like this: 1, 2, 3, 4, 5. Then I'll just work the rest out. Well, on the first carbon, I have an alcohol. So there we go. And if you need to number your carbons, hey, by all means, 1, 2, 3, 4, 5, no problem. Just go ahead and do it, okay? What else? On carbon 3, we've got a methyl group. So let's put that in. I'll erase the number 3, throw the methyl group in like that. There you go. You're done. Now it's asking us to write a condensed structural formula. These are, they're interesting sometimes. I'm going to start from this end. Okay, I'm going to start from that end and write down the condensed structural formula. So look, I've got the CH3. Okay, so that's this one. Now I've got the CH2. That's this methylene right here. Then I have CH. Okay, it's got a methyl group attached to it. Since the methyl is smaller, I'm going to put it in brackets like that. Next, I have another methylene. Okay, and I have another methylene. And then I have my hydroxyl, like that. So there you go. That's the condensed structural formula of that compound. Next, we're asked to draw structures of the following molecules. Let's do the first one, 4-methoxyoctanol. There's an error here. There shouldn't be a space there technically, but whatever. So why don't we start by drawing the parent, octanol. So let's start by drawing octanol, which is an aldehyde. So it's got 1, 2, 3, 4, 5, 6, 7, 8 carbons in it like this. Then we have a 4-methoxy. What's a methoxy? It's when you have a methyl with an oxygen directly attached to it like that. So if we count 1, 2, 3, here's the 4th carbon. We're going to put our methoxy group on there. You can write OCH3 if you want. You just want to draw it as a bond line structure and put O and draw the methyl like that. Perfectly reasonable. Perfectly correct. Next, we have 3-methyl 2-pentanol. Take the same approach. So we'll start with 1, 2, 3, 4, 5 carbons, right? We have a pentane. And on the second carbon, we're going to have our hydroxyl. So that's a 2-pentanol. On the third carbon, we're going to have a methyl group, right? 1, 2, 3, 4, 5. On carbon 2, we have our hydroxyl. And on carbon 3, we have a methyl group. So 3-methyl-2-pentanol. And the last one is another one that's got a gap in it. It shouldn't have a space here. It should just be 2-ethoxybutane. Anywho, let's start by drawing the structure. So we got butane. So that's 1, 2, 3, 4. And on the second one, we're going to have an ethoxy. What's an ethoxy? It's an ethyl group with an oxygen attached to it like that. So we're going to have our oxygen, and then we're going to have 1, 2 carbons like that. Here we go, 2-ethoxybutane. And if you want to put a shorthand, if you want to write OET, ET is a shorthand for ethyl, that's fine. If you want to write the whole thing out, write CH2, CH3, I don't mind it if my students combine condensed and bond line structures, as long as they get the right answer. Right? That's the main thing. My students understand what the heck is going on. Okay, number 25, circle the molecule that's going to be most soluble in water. I'm going to draw these kind of quickly. The first one is 2-isopropyl-hexane. We have 1, 2, 3, 4, 5, 6. On the second carbon, we have an isopropyl group. Then we have 4-tert-butyl-1-pentanol. So we have 1, 2, 3, 4, 5 hydroxyl here. And on the second carbon, we've got a tert-butyl. Kind of running out of space here. There we go. And the last one is nonenal. So we got nonenal. So it's got 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, if I look at nonenal, it's got 9 carbons in it. 2-isopropyl-hexane has 6, 7, 8, 9 carbons in it. And 2-tert-butyl-1-pentanol has 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. They have 9 carbons in them. Okay, the first one is a hydrocarbon. That's totally nonpolar. Now, the aldehyde is polar, right? It's got a polar group here. But what advantage does the pentanol have? Can anybody tell me?
It doesn't have a double bond?
No, it's got nothing to do with a double bond. Remember the rule, like dissolves like? So it's in water, so like dissolves like. This molecule is capable of hydrogen bonding, right? So this can H bond or hydrogen bond. And so the answer is going to be the alcohol, right? Water has 2 hydroxyls in it, technically, right? So water can hydrogen bond and the alcohol can hydrogen bond. All right. Draw the reaction that converts propene to isopropanol. I mean, this is a question you'd never be asked in this way because our exam is multiple choice. But basically what they're getting at is if you start with propene, okay, and then you convert that to isopropanol. Like this is isopropanol. The idea is that you recognize that this is a Markovnikov addition. Okay, this is clearly a Markovnikov addition, right? The rich are getting richer. This carbon only has 1 hydrogen, and this carbon has 2 hydrogens. Now it's got 3 hydrogens, okay? So the rich are definitely getting richer here. How do we do a Markovnikov addition? Well, the conditions that we need are simply acid and water. Nothing more than that. If you wanted to just write hydronium, if you just write H3O plus, I would accept that too. That's perfectly fine. Okay, let's try number 27. Draw an example of a hydrogen bond between ethanol and water. Look, I would expect anybody in this class to be able to go up to a student who's in chemistry 101, and teach them about hydrogen bonding and, represent a molecule of ethanol. So first I'll draw ethanol, so here's my ethanol molecule, ethanol. I'll draw a water molecule like this, and you could draw them any which way you want. But remember that the oxygen is delta minus, right? In both of these, oxygen is the second most electronegative element in the periodic table. The hydrogens are going to be delta plus, right? They're going to be starved for electron density because it's going to be mostly pulled towards the oxygen. And when we want to show a hydrogen bond, we show it from the hydrogen to the lone pair on the oxygen like that. We could draw another one like this. Okay, so that would be a representation of hydrogen bonding between ethanol and water. And here's, I'm showing 2 hydrogen bonds. Anyhow, this is a kind of a funny problem, okay? I like this one. It says, which would be expected to undergo dehydration at a lower temperature? A primary, secondary, or tertiary alcohol? Not a simple question, but I want to go over the theory of it with you so that you understand, because you do have to understand Zaitsev products, okay? Let's say we had a primary alcohol like 1-propanol. So this is the primary alcohol. Let's say we had a secondary alcohol like 2-butanol. So this is the secondary alcohol. And let's say we had a tertiary alcohol like, oops, I'm getting ahead of myself here. Let's say we had a tertiary alcohol like 2-methyl-2-butanol. Okay, so this is tertiary. Well, if you think about these undergoing dehydration, right? If this one underwent dehydration, this is the only thing that could form. This molecule, if it underwent dehydration to form the Zaitsev product, you'd get this, okay? And I could have drawn it trans or cis, I don't care. That's neither here nor there, okay? So you'd get something that looks like this. And again, I'm drawing the Zaitsev products. If you were to dehydrate this, you'd end up with something that looks like this. So what's the difference between these 3 alkenes, right? If I examine the 2 carbons in each one of these double bonds, right? This is a CH2, this is a CH. That double bond, those 2 carbons are only bound to 1 carbon. This is a CH, this is a CH. If you look at those 2 carbons, they're only bound to 2 carbons. Whereas in the third one, the tertiary alcohol, this is a CH, this is a C, just a quaternary carbon. That double bond overall, it is attached to 1, 2, 3 carbons. So this one is tri-substituted. It gives the most substituted alkene. Okay? So the tri-substituted alkene, it is the most stable of all these alkenes. And if it's more stable, then it's going to be formed first. Okay, it's going to undergo dehydration at a lower temperature. The activation energy won't be as high. It's another way to put it. Okay, the activation energy is just lower. All right, so kind of a conceptual question and a fun question. Well, let's get some more practice in drawing dehydration products. Here they're asking you to draw the product of treating this alcohol. So this is a secondary alcohol. This is 2-hexanol. 2-hexanol. We're treating that with acid, and we're going to heat that up, right? And we're going to lose water in the process. Where's the water going to come from? It's going to come from the hydroxyl. Here's the carbonyl carbon. You go to this carbon, which is next door, and you go to this carbon, which is next door. If you were to pull a proton from the methyl group, you'd put the double bond here. If you were to pull a proton from this methylene here, you'd put the double bond there. So let's draw the 2 possible products. First, I'll draw the one that if you took the proton from the CH2 or the methylene, you'd end up with this molecule. And if you took the proton from the methyl group, you'd end up with this 1, 2, 3, 4, 5, 6. You'd end up with this. Who could tell me which one of these would be the major product, the blue one or the red one? Not a trick question. Yes, right, this is going to be the major product. Maybe I should be color coordinated here. So this would be the major product. This would be the minor product. Right, this would be the Zaitsev product. Okay, this has a name. It's called the Hoffman product. It's never going to come up on your final. Anyhow, there we go. All right.